Right, conservative and non-conservative forces. We'll start with conservative. Conservative force is one in which the work, just the work, does not depend on the pathway taken. Let's see. Props. Here we go. The best example of this is probably the gravitational force, but the elastic force is also held up as an example of it quite frequently. So let's talk gravitational force. Let's say you start with a ball, and it starts at some position and you lift it to some higher position. In that process, there's some negative work done by the gravitational force. If you start at that same position and you go in some weird circuitous path, get to the same height, it's still going to be the same amount of work. So if I drew something like that, we can show that taking a ball from one location and lifting it up to another, just motion straight up. Work will be mg delta y. The x component wouldn't matter if we take and move it specifically in some complicated path that takes us ultimately to the same position, this time moving along x. So we have a delta x, and moving along y, so we have a delta y. Well, the gravitational force is pure vertical. If we take the dot product, the horizontal component doesn't matter. It only depends on mg and delta y. And in fact, this stuff where I go up and down and up and down and up and down before finally stopping doesn't matter at all. It really is just the endpoints that matter. How do we know? Well, all this stuff in the middle, for every point where we're going up, there's a point where we're going down until we finally get to our destination. So all this stuff that's in the middle here, in the middle here, I'll do it in a different color. Pretty much everything in here matters not the slightest to the motion. It's just a straight up rise as far as things are concerned. So we really only care about the initial and final locations, the very definition of a conservative force. What is a non-conservative force? Well, in a non-conservative force, the work depends on the path taken. You might be thinking, well, wait, if elastic and gravitational don't work this way, if they don't depend on the path taken, then doesn't nothing? Well, there are things that absolutely depend on the path taken. Resistive forces and friction depend on the path taken. Let's talk about why. Okay. So now let's say we've got some object and we're going to slide it along a table. So I'll use a stapler and this thing to represent a table and the object. If we take the object and we slide it straight across, then the friction force is always back in the opposite direction we're traveling. But what if we take the object and we go in this big old loop shape to get there? Well, the friction force always opposes the direction of motion at each point along the path. Let's draw that out. So here, we're going to set up a tabletop. And we're going to start with an object at some position on it. We're going to consider one path where we simply go straight across. So we have an initial and a final. At each point as we go along here, the friction force, we'll call it F sub k, is acting against our motion here. Oops, I thought I'd changed to yellow. And there. Actually, I need yellow anyway. And what if we take a path like this? Well, along this path, the friction force is pointed against our motion at any point. So notice that as far as this is concerned, one of them is going to look like Fk with a minus sign in front because we'll get cosine of 180 times y final minus y initial, just a simple delta y. But if we take this other path, which is basically a semicircle, and we look at the work done in this case, we're going to have a minus Fk. It always opposes where we're going. And then it is basically going to be, this is the diameter, so pi times d would be the whole way around. This is basically going to be pi over 2 delta y instead of just delta y. We end up doing more work in the case where we travel longer against it. Well, shoot. All right, I'm going to draw the picture out again. You can kind of skip ahead. I don't have the time to re-record today, unfortunately, so you're getting what you're getting. All right, our tabletop, our object. We're first going to try and take it directly across from some y initial to y final. The work in that case will be a minus Fk delta y. Then we're going to take a semicircular path. Along the original path at each point, the friction force just opposes the motion, so Fk is simple, and the path is simple. Along this curved path, Fk ends up being in some pretty crazy directions, depending on where we are at any given moment. But the thing that remains consistent is that it opposes our motion at every point. So in this second case, the work ends up being minus Fk. This is a semicircle, so pi times the diameter would be the full circumference. We want half of that. It's basically, pi over 2 delta y. It's more work for the longer path. So the work doesn't just depend on yi and yf anymore, it depends on the path. And if we took some really wild path that wiggled back and forth a bunch of times, we could end up with a lot more work being done by friction, because it will always turn to oppose our direction of motion. Okay, so sorry about the lost minute there. Could have made this video shorter. If I get a chance in the future, I'll try and re-record for future classes, but I'm afraid classes this semester, you're going to have to deal with it, and potentially future classes will as well until I have the time to fix this. But we will stop there about 8 minutes in. That is conservative and non-conservative forces.